Suppose I told you there is one equation, just one, that describes nearly everything you have ever seen, heard, touched, or measured. Every flash of lightning, every color in a sunset, the reason your hand does not pass through a table, the reason the sun burns, the reason a magnet sticks to your refrigerator, all of it packed into one single equation, small enough to fit on a coffee mug. You would think I was out of my mind, right? And yet, that equation exists. We wrote it down. Physicists have tested it to extraordinary precision. And here is the disturbing part. It is almost certainly incomplete. Something enormous is missing. That is what I want to talk to you about today. By the time we are finished, you will understand what that equation actually says. In plain English, no PhD required. You will understand why it is the greatest achievement in the history of physics. And you will understand why it keeps me up at night, because what it leaves out might be more important than what it includes. Let me start with something simple, something you already know, even if you do not realize you know it. You throw a ball, it goes up, it comes back down. You have been watching this since you were 2 years old. Nothing remarkable about it. But here is the thing. That ball, while it is in the air, is obeying a law. It is not choosing to come down. It is not deciding to follow a curve. Something is making it do that. And the question is, what? Now, if you ask Newton, he would say, easy. There is a force pulling it down, the force of gravity. And my law says F equals m times a. Force equals mass times acceleration. That is the rule, and that is wonderful. It really works. You can calculate where the ball will land. You can aim cannons with it. You can send rockets to the moon with it. Beautiful. But here is what always bothered me, even as a kid. Newton tells you the ball follows a particular path. It goes up in this curve and comes down. Fine. But why that path and not some other path? What is special about the actual path the ball takes compared to all the other paths it could have taken? You see, that is a strange question. Most people do not ask it. They say, well, it follows Newton's law, that is why. But that is like saying it does what it does because it does what it does. I want a deeper reason, and it turns out there is one. A beautiful one. A shocking one. The actual path the ball takes is the one that makes a certain number as small as possible. There is a quantity, a single number, computed along the entire path of the ball, and nature chooses the path that minimizes that number. We call that number the action. And the rule is called the principle of least action. Now wait, let that sink in for a moment. I am not telling you what force pushes or pulls the ball at each instant. I am telling you something much more strange. I am telling you that nature somehow looks at all possible paths the ball could take, every single one, every crazy zigzag and loop and detour, and it picks the one path that makes this special number the smallest. As if the ball, before it moves, surveys every possibility and selects the best one. This is a completely different way of thinking about physics. Newton says, look at the ball at this instant. What force is on it, that determines what it does next. That is a local way of thinking, step by step, moment by moment. But the principle of least action says, look at the whole trip. Look at where the ball starts and where it ends. Among all the ways it could get there, it picks the way that minimizes the action. That is a global way of thinking. It sees the whole journey at once. And here is the remarkable thing. Both descriptions give you exactly the same answer. Newton's law and the principle of least action are mathematically equivalent. They are two different ways of saying the same thing, like two different languages describing the same sunset. But, and this is the crucial but, the principle of least action turns out to be far more powerful. It generalizes. Newton's law works beautifully for balls and planets and cannonballs, but when you get to electricity, magnetism, light, atoms, nuclear forces, the particles inside the nucleus, Newton's specific formula does not work anymore. You need different equations for each of those. However, the principle of least action works for all of them, every single one. You just have to change what goes inside the action. You change the recipe, but the principle stays the same. Let me say that again because it is worth repeating. The principle of least action is the one idea that underlies all of physics, all of classical mechanics, all of electromagnetism, all of general relativity, all of quantum field theory. Every fundamental theory we have discovered obeys this principle. That is not something we demanded ahead of time. That is something nature showed us, again and again and again. Now, I want to take a little detour, because this idea, this principle of least action, has a history, a wonderful history, and it shows you something about the way physics progresses, which is never in a straight line. The first person who really saw this principle was a Frenchman named Pierre de Maupertuis back in the 1740s. He had a somewhat mystical interpretation of it. He thought God, being perfect, would obviously design a universe that minimized effort. That was his reasoning. Not very scientific, but he had the right instinct. Later, Euler and Lagrange put the mathematics on a solid footing, and by the 1800s, William Rowan Hamilton had turned it into a complete mathematical framework. But here is the funny part. For a long time, people treated the principle of least action as a curiosity, a clever reformulation, nice for mathematicians, practically useless. Newton's F equals ma was the workhorse. You had a force, you computed the acceleration, you solved the equation. That was physics. The Lagrangian approach was considered a luxury. And then, in the 20th century, everything flipped. It turned out that the Lagrangian approach was not a luxury. It was the only approach that worked for the new physics. When you try to write down the laws of electromagnetism or general relativity or quantum field theory in Newtonian language, it is a nightmare. The equations are tangled, the symmetries are hidden, and the whole structure is obscure. But in Lagrangian language, everything becomes transparent. The symmetries are manifest, the structure is clear, and the generalizations leap off the page. It is as if, for 2 centuries, we had been building houses with a hammer, and then someone invented the power drill, and suddenly we could build skyscrapers. The Lagrangian formulation was the power drill of modern physics. Every major advance of the 20th century used it. And it all started with that simple question, what quantity does nature minimize? So now you might be wondering, what exactly is this action thing? What goes inside it? Well, the action is computed from something called the Lagrangian. This is a function, a recipe, if you like, that tells you at every point in space and time what the system is doing. For a ball in the air, the Lagrangian is just the kinetic energy minus the potential energy. Kinetic energy, that is the energy of motion. Potential energy, that is the energy of position, like how high up you are. You take the difference, kinetic minus potential, at every instant, and you add it all up along the path. That sum is the action, and nature minimizes it. Now, here comes the real story, the one I have been building toward, because what I have told you so far is classical physics. It is beautiful, but it is old news. The new thing, the thing that shakes you to your bones, is what happens when you ask what Lagrangian describes not just balls and planets, but everything. Every particle, every force, every interaction in the universe. But before I answer that, let me tell you how we got there. Because the story of unification is one of the most thrilling stories in all of science, and you cannot appreciate the ending unless you know the beginning. In the 1860s, James Clerk Maxwell did something extraordinary. At the time, people knew about electricity, they knew about magnetism, and they knew about light. 3 separate phenomena, 3 separate sets of experiments, 3 separate chapters in the textbook. Maxwell sat down and wrote 4 equations that described electricity and magnetism together as one unified field. And when he solved his own equations, he found that they predicted waves of oscillating electric and magnetic fields, propagating through space at a speed that you could calculate from electrical measurements done in a laboratory. And when he calculated that speed, it came out to be 186,000 miles per second, the speed of light. Maxwell did not go looking for light. He went looking for the connection between electricity and magnetism, and light fell out of the equations as a gift, a free bonus. Unification gave him more than he asked for. That is a pattern we will see again and again. Now, fast forward 100 years. By the 1960s, physicists had identified 4 forces of nature: gravity, electromagnetism, the strong nuclear force, which holds the nuclei of atoms together, and the weak nuclear force, which is responsible for certain kinds of radioactive decay, like when a neutron turns into a proton, an electron, and a neutrino. These 4 forces looked completely different. Gravity is long-range and feeble. Electromagnetism is long-range and much stronger. The strong force is incredibly powerful, but operates only over distances smaller than an atomic nucleus. The weak force is feeble and also short-range. 4 forces, 4 different strengths, 4 different ranges, 4 different characters. It seemed like nature had thrown 4 completely separate ingredients into the pot. But then Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that electromagnetism and the weak force are actually the same force. At low energies, they look different, just as ice and steam look different, but at high energies, they merge into a single electroweak force. The reason they look different at ordinary energies is because of the Higgs field, which I will tell you about shortly. The Higgs field breaks the symmetry and splits the electroweak force into the 2 pieces we observe: electromagnetism, carried by the massless photon, and the weak force, carried by the very heavy W and Z bosons. That was another unification. Electricity and magnetism had already been unified by Maxwell. Now the electromagnetic force was unified with the weak force. 3 forces reduced to 2. And once again, the unification predicted new things. It predicted the existence of the W and Z bosons, and it predicted their masses. And when the experiments were done at CERN in the early 1980s, there they were, exactly as predicted. So now the question is obvious. Can we go further? Can we unify the electroweak force with the strong force? Can we get all 3 standard model forces from a single symmetry, and can we then bring gravity into the fold? That is the dream, the impossible dream. And the answer is, we found one. We actually found one. It is called the Standard Model Lagrangian, and it is the equation I was talking about at the beginning. The one that fits on a coffee mug. Now, let me be honest with you. When you see this equation written out, it does not look simple. It takes up maybe half a page of dense mathematical symbols. Greek letters, subscripts, superscripts, summation signs, things most people would run screaming from. But here is the thing that is extraordinary. Despite how complicated it looks, it has a structure that is breathtakingly elegant. And I can tell you what it says in plain words. The Standard Model Lagrangian tells you 4 things, just 4. First, it tells you what particles exist. Second, it tells you what forces exist. Third, it tells you how those particles interact with those forces. And fourth, it tells you how particles get their mass. That is it. Those 4 ingredients, written down in one Lagrangian, plugged into the principle of least action, give you every prediction we have ever made about the behavior of matter and energy, except for gravity. And every single one of those predictions has turned out to be correct. Some of them to 10, 11, 12 decimal places. The most precisely tested theory in the history of science. Let me give you one example, because it is a good one. It involves the electron. The electron has a property called a magnetic moment. Roughly speaking, the electron behaves like a tiny magnet. Now, Dirac's equation, the equation that combines quantum mechanics with special relativity, predicts that the magnetic moment of the electron should be exactly 2 in certain natural units. But when you do very precise measurements, the magnetic moment is not exactly 2. It is slightly more than 2. The difference is tiny, something like 0.00116. Where does that tiny deviation come from? It comes from quantum corrections, from the fact that the electron, as it sits there being an electron, is constantly emitting and reabsorbing virtual photons. virtual electron-positron pairs, virtual everything. All these quantum fluctuations shift the magnetic moment by a small amount, and we can calculate that shift using the Standard Model to extraordinary precision. The theoretical prediction and the experimental measurement agree to better than 1 part in a trillion. That is like predicting the distance from New York to Los Angeles to within the width of a human hair. I do not know of any other theory in any field of science that makes a prediction that precise and gets it right. That is the Standard Model at its best. That is what the equation on the coffee mug gives you. Let me walk you through it. Do not worry. I will keep the symbols to an absolute minimum. What matters is the ideas. The first piece of the Standard Model is the particles. These are the things the world is made of, and there are remarkably few of them. You have quarks, which come in 6 flavors: up, down, charm, strange, top, bottom, silly names. Physicists are not good at naming things. Then you have leptons. The electron is a lepton. So is the muon and the tau, and each of these has a corresponding neutrino. So 6 quarks, 6 leptons. That is 12 matter particles. Everything you see around you, every atom, every molecule, every star, every person, is built from just 2 of these: the up quark, the down quark, and the electron. The other 10 are heavier copies that show up briefly in particle collisions and then decay away. The second piece is the forces, and here is where it gets interesting. In the Standard Model, forces are not mysterious pushes or pulls. Forces are carried by particles. Think of it this way. Imagine 2 ice skaters facing each other on a frozen lake. One of them throws a basketball to the other. When the first skater throws the ball, she recoils backwards. When the second skater catches it, he gets pushed backwards too. By exchanging the ball, they have exerted a force on each other, a repulsive force. That is essentially how forces work in particle physics. Particles exchange other particles, and that exchange is the force. The electromagnetic force, which holds atoms together and makes light, is carried by the photon. The strong force, which holds quarks together inside protons and neutrons, is carried by particles called gluons. There are 8 types of gluons. The weak force, which is responsible for certain kinds of radioactive decay, is carried by 3 particles: the W+, the W-, and the Z. So the force carriers are the photon, 8 gluons, and the W+, W-, and Z, 13 force-carrying particles. Now, the third piece of the equation tells you how these particles interact. And this is where the magic is. The interactions are not arbitrary. They are completely determined by a single idea: symmetry. Let me explain what I mean. Suppose you have a physics experiment. You do it in your laboratory, and you get some result. Now you pick up the whole laboratory and you move it 10 feet to the left. Do you get a different result? No. The laws of physics do not care where your laboratory is. That is a symmetry. It is called translational symmetry. Now suppose you rotate your laboratory by 30 degrees. Same result? Yes. That is rotational symmetry. Suppose you wait 5 minutes and then repeat the experiment. Same result? Yes. That is time symmetry. These are the obvious symmetries, the ones everybody knows about. But hold on. I have not told you the punchline about these obvious symmetries. There is a theorem proved by a brilliant mathematician named Emmy Noether that says every symmetry of the Lagrangian corresponds to a conservation law. That is not just a pretty statement. It is exact, it is mathematical, and it is profound. Translational symmetry, the fact that the laws of physics do not depend on where you are, gives you conservation of momentum. Rotational symmetry, the fact that the laws do not depend on which way you are facing, gives you conservation of angular momentum. Time symmetry, the fact that the laws do not change from one era to the next, gives you conservation of energy. Think about that for a moment. The reason energy is conserved, the reason you cannot build a perpetual motion machine, the reason you get tired when you run, is because the laws of physics are the same today as they were yesterday. If the laws were changing, energy would not be conserved. The conservation law flows directly from the symmetry as inevitably as water flows downhill. And Noether proved this, not for these three examples, but for any symmetry of any Lagrangian. Every symmetry gives you a conservation law. Every conservation law comes from a symmetry. This is one of the deepest results in all of theoretical physics. And it means that when we talk about the symmetries of the Standard Model, we are not talking about decoration. We are talking about the scaffolding. The symmetries are what hold everything together, but the Standard Model has additional symmetries, hidden ones, internal ones, symmetries that do not involve moving through space or time, but involve transforming the mathematical fields that describe the particles. And these internal symmetries are what dictate the forces. Let me try an analogy. Think of a compass needle. It points north. Now imagine you could change what north means at every single point in space, independently. You are allowed to redefine the direction of north differently at your left hand and at your right hand, differently at your head and at your feet, differently here and a mile away. If the laws of physics have to still work the same way after all these local redefinitions, then something interesting happens. You are forced to introduce a new field, a new particle, whose job is to keep everything consistent despite the local changes. That new field is the force carrier. This is the deep idea. The photon exists because of a symmetry. The gluons exist because of a symmetry. The W and Z bosons exist because of a symmetry. The symmetries of the Standard Model are described by a mathematical group called SU3 times SU2 times U1. Now, those symbols do not matter for our purposes. What matters is the idea that the forces of nature are not accidental. They are required by symmetry. They have to be there. This is, I think, one of the most beautiful things human beings have ever discovered. The forces that hold the world together are consequences of abstract mathematical symmetries. As if the universe was designed by a mathematician with a taste for elegance. Now, I do not mean that literally. I do not know who designed what, but the structure is there, and it is gorgeous. Now, let me pause here and do my check. Let me make sure I am being clear. If you were a bright 12-year-old and you asked me what is the Standard Model, I would say this. The Standard Model is a recipe. You list the ingredients, which are a small number of particles. You list the rules, which come from symmetry. And you write down one equation, one Lagrangian, that captures all of it. Then you feed that equation into the principle of least action, and out comes every prediction about how particles behave. It is like a cookbook, but for the universe. Good. Now, there's a common misconception I want to address. A lot of people hear one equation that describes everything, and they think it means we can predict everything, that we can calculate the weather next Tuesday, or what you will have for lunch, or whether a particular radioactive atom will decay in the next 5 minutes. And that is completely wrong. Here is why. Even though we know the fundamental equation, the calculations are, in almost every practical case, impossibly hard. Let me give you an analogy. You know the rules of chess. Every rule. You know how each piece moves, what constitutes a legal move, what constitutes checkmate. You know the complete rules of the game. Does that mean you can beat a grandmaster? Of course not. Knowing the rules and being able to calculate the consequences of the rules are two entirely different things. In physics, the same thing happens. We know the Lagrangian, we know the equation, but solving it for a system of many particles is staggeringly difficult. The quantum mechanical equations for just a single atom of iron with its 26 electrons are essentially unsolvable by brute force. And you want me to predict the weather? You are asking me to solve the equations for something like 10 to the 25th particles all interacting at once. That is not a failure of the theory. That is a practical limitation. The equation is right, we just cannot compute fast enough. And here is an even deeper point. In quantum mechanics, there is genuine randomness. Not randomness because we are ignorant, but randomness that is built into the fabric of reality. When a radioactive atom decays, there's no hidden clock inside it ticking down. There's no way, even in principle, to predict exactly when it will happen. The equation gives you the probability. It does not give you the certainty. So even with the perfect equation and infinite computing power, you still could not predict everything. Now, let me take you on a thought experiment. This is my favorite part. I want you to imagine something strange, something that might seem crazy, but is actually the way quantum mechanics works. Forget the ball I was talking about earlier. Instead, think about an electron. It starts at point A and it ends up at point B sometime later. In classical physics, it follows one path, the path that minimizes the action. But in quantum mechanics, here is what really happens. The electron takes every path, simultaneously. Every possible path from A to B, the straight line, a loop-de-loop, a path that goes to the Andromeda Galaxy and back, a path that zigzags 1 trillion times. Every path you can imagine, and infinitely many you cannot. Now, each path contributes a little arrow, a little complex number to the total. And you add up all these little arrows from all possible paths, and the result tells you the probability that the electron gets from A to B. This is the path integral. This is the way I reformulated quantum mechanics in my thesis work. And here is the beautiful thing. For most of the crazy paths, the little arrows point in random directions. They cancel each other out. The arrow from the path that goes to Andromeda and back almost exactly cancels the arrow from a path that goes to Andromeda and takes a slightly different route back. They cancel only the paths near the classical path, the one that minimizes the action, have arrows that line up, that add constructively. So the total sum is dominated by the contribution from the region near the classical path. That is why, in everyday life, things look classical. The ball appears to follow one path, because for a heavy object, the arrows from the far-out crazy paths cancel so thoroughly that only the action-minimizing path survives. But for a tiny thing like an electron, the cancellation is not so thorough. The electron genuinely explores many paths. It really does go many ways at once. And this is not philosophy. This has measurable consequences. The double-slit experiment proves it. Let me push this a little further, because it is too beautiful not to. You shoot electrons, one at a time, at a barrier with 2 slits. Each electron goes through one slit or the other. At least, that is what common sense says. But when you collect the electrons on a screen behind the barrier, they do not form 2 simple blobs, one behind each slit. Instead, they form a pattern of bright and dark bands, an interference pattern, the same kind of pattern you get when 2 water waves overlap. Bright where the waves add up, dark where they cancel. But wait! You sent the electrons one at a time. There was only one electron in the apparatus at any moment. It could not have been interfering with another electron. It was interfering with itself. Its quantum wave, its collection of arrows from all possible paths, went through both slits at once. And the arrows from the paths through the left slit and the paths through the right slit interfered with each other, some adding and some canceling, creating the pattern. Now, if you try to peek, if you put a detector at one of the slits to see which slit the electron went through, the interference pattern disappears. The act of measurement collapses the sum over paths. You force the electron to choose one path, and the beautiful pattern is destroyed. That is quantum mechanics in its starkest form. The electron takes all paths until you look, and then it takes one. I remember being stunned by this when I first worked it out. You have a formalism, a mathematical apparatus, the path integral, that says sum over all histories. Every possible thing that could happen, add it all up. And from that insane instruction comes the real world. Every experimental result we have ever measured. It sounds like madness, and it is. But it works. So here is the picture. The fundamental description of nature is not a particle follows a single path determined by forces. The fundamental description is a particle explores all paths, weighted by the action, and the probabilities emerge from the sum. The principle of least action, which seemed like a strange global principle in classical physics, turns out to be the natural classical limit of the path integral in quantum mechanics. In quantum mechanics, All paths contribute. In classical mechanics, only the path of least action survives. It is not that nature is minimizing anything on purpose. It is that the quantum sum, when you look at it from far away, when the objects are big and heavy, automatically concentrates around the classical path. The principle of least action is not a separate postulate. It is a consequence of quantum mechanics. That, to me, is one of the most profound things in all of physics. Now, let me get back to the Standard Model, because I owe you the fourth piece. I told you the equation tells you four things: particles, forces, interactions, and mass. I have covered the first three. The fourth one is special, and it was the last piece to be discovered. Here is the problem. The symmetries of the Standard Model, the ones I told you about, the ones that dictate the forces, those symmetries have a built-in implication. The particles should all be massless. Every one of them. The photon, the electron, the quarks, the W boson, all of them. They should have zero mass and travel at the speed of light. And obviously that is wrong. The electron has mass, quarks have mass, the W and Z bosons are very heavy. Something has to break the symmetry, but you have to break it delicately. You have to break it in a way that does not destroy the good things the symmetry gives you, like the consistency and mathematical soundness of the theory. You have to break it softly. And the mechanism for doing this involves a field that fills all of space, a field that is not zero even in the vacuum. Even in empty space, this field has a non-zero value. And when particles move through this field, they interact with it, and that interaction gives them mass. Heavy particles interact strongly with this field. Light particles interact weakly. The photon does not interact with it at all, which is why the photon is massless. This field is called the Higgs field. And the ripple in this field, the quantum excitation of it, is a particle called the Higgs boson. When you disturb the Higgs field just right, you get a Higgs boson. Just as when you disturb the electromagnetic field, you get a photon. And when you disturb the surface of a pond, you get a wave. The Higgs field was proposed in the 1960s, and for decades it was the one piece of the Standard Model that had not been confirmed experimentally. The big particle colliders had not yet reached high enough energies to create the Higgs boson, but the theory predicted it should exist, and the theory predicted approximately how heavy it should be. So the whole world waited, and it was found. The experiments confirmed it. The last piece of the Standard Model fell into place. The equation was complete. So you might be thinking, wonderful, we have the equation, we won. The story is over. And if that were the case, I would not have called this lecture The Impossible Dream, because here is where the trouble begins. The Standard Model, for all its glory, is not the whole story, not even close. And the things it leaves out are not small, obscure, technical details. They are enormous, gaping holes. The first one, gravity. The Standard Model describes three forces: electromagnetism, the strong force, and the weak force. But there are four forces in nature. The fourth is gravity. And gravity is not in the equation. Not anywhere. The Standard Model Lagrangian says nothing about why apples fall from trees, nothing about why planets orbit stars, nothing about why galaxies hold together. Gravity is described by a completely separate theory, Einstein's general relativity, which says that gravity is not a force at all, but the curvature of space and time caused by mass and energy. And that theory works beautifully on its own for large things, planets and stars and galaxies. But here's the problem. We do not know how to combine them. When you try to write a quantum field theory of gravity, the same way we have a quantum field theory of the electromagnetic and nuclear forces, the mathematics blows up. You get infinities that you cannot get rid of. The tricks that work for the other forces, the tricks of renormalization that allow us to extract finite answers, those tricks fail for gravity. So we have two theories: the Standard Model for the small stuff and general relativity for the big stuff. And they do not talk to each other. They are written in different mathematical languages, they obey different principles, and when you try to merge them, you get nonsense. That is like having two maps of the same city drawn on different scales, in different projections, And when you try to overlay them, they do not match. There is something missing, something we do not understand yet. The second problem, dark matter. When astronomers look at galaxies and measure how fast the stars at the edge are rotating, they find something shocking. The stars are moving too fast. Based on the visible matter in the galaxy, the stars should be flying off into space. There is not enough gravitational pull to hold them in. But they are not flying off. Something invisible is holding them in. Something that has mass, that exerts gravity, but that does not interact with light. We call it dark matter because we cannot see it. And it is not a small thing. There is about 5 times more dark matter in the universe than ordinary matter. 5 times! Everything you see, every star, every planet, every person, all of it is only about 15% of the matter in the universe. The rest is dark. And the Standard Model has no particle that could be dark matter. Nothing in the equation accounts for it. The third problem, dark energy. In the 1990s, astronomers discovered that the expansion of the universe is accelerating. The galaxies are not just moving apart, they are moving apart faster and faster. Something is pushing the universe apart. Some kind of energy that fills all of space and causes repulsive gravity. We call it dark energy. And it is the dominant component of the universe. About 70% of the total energy content of the universe is dark energy. And we have almost no idea what it is. The Standard Model does not explain it. So let me add this up for you. The Standard Model beautifully describes about 5% of the energy content of the universe. 5%. The rest, dark matter and dark energy, is a mystery. The equation on the coffee mug accounts for 1/20th of what is out there. If that does not keep you up at night, you are not paying attention. But wait, there is more. Even within its own domain, the Standard Model has strange features that cry out for explanation. Why are there 3 generations of quarks and leptons? Why not 1? Why not 17? The equation does not tell you. You just have to put in the number 3 by hand. Why do the particles have the masses they have? The electron is about 2,000 times lighter than the proton. Why? The equation does not predict those masses. You have to measure them and plug them in. There are about 19 free parameters in the Standard Model. Numbers that are not predicted by the theory but have to be determined by experiment. Coupling constants, mixing angles, masses, and nobody knows why those numbers have the values they do. There is also the problem of matter and antimatter. The Standard Model says that in the early universe, matter and antimatter should have been produced in nearly equal amounts. And when matter meets antimatter, they annihilate each other and produce pure energy. So where is all the antimatter? Why is the universe made almost entirely of matter? There is a tiny asymmetry built into the weak force, a thing called CP violation, but it is not nearly enough to explain the overwhelming dominance of matter that we observe. Something else must be going on. And then there is the question of neutrino masses. The original Standard Model assumed neutrinos were massless, but experiments have shown that neutrinos do have mass, albeit very tiny mass. The equation has to be modified to accommodate this, and the simplest way to do it introduces new particles and parameters that are not in the original formulation. So even the equation on the coffee mug is, strictly speaking, already out of date. So here we are. We have the most successful equation in history, the most precisely tested, the most broadly applicable, the most compact summary of natural law ever devised. And yet it describes only a fraction of the universe. It is silent about gravity. It cannot explain its own parameters. And it has been caught by surprise by neutrino masses and the accelerating expansion of space. This is what I mean by the impossible dream. The dream is to find one equation, truly one equation, that describes everything. Not almost everything. Not everything except gravity. Not everything except dark matter. Everything. And we are not there. We may not be close. Now, people have tried. Oh, how they have tried. There are proposals, grand unified theories, which try to merge the 3 Standard Model forces into one. Supersymmetry, which proposes that every particle has a heavier partner doubling the number of particles but gaining mathematical elegance. String theory, which proposes that all particles are really tiny vibrating strings and that different vibration patterns correspond to different particles, and that there are extra dimensions of space curled up too small for us to see. Loop quantum gravity, which tries to quantize space itself, making it discrete at the tiniest scales. These are all interesting ideas. Some of them are beautiful, some of them make predictions, but none of them have been confirmed by experiment, not one. And in physics, no matter how beautiful your theory is, if it does not agree with experiment, it is wrong. That is the rule. That has always been the rule. So what do we do? What is the right attitude to take? I think the right attitude is this. We should be proud of what we have. The Standard Model is a magnificent achievement. It represents centuries of work by thousands of brilliant people. It captures deep truths about nature. The idea that symmetry dictates the forces, the idea that the vacuum has structure, the idea that particles are excitations of fields. These are genuine insights into the way the world works. We should celebrate that. But we should also be honest about what we do not know. And we should not pretend that beauty and elegance are substitutes for experimental evidence. I have seen physicists fall in love with their theories and lose touch with the data. That is dangerous. Physics is not mathematics. Physics is about the real world, and the real world has the final say. You know, there is a funny thing about the history of unification in physics. Every time someone has successfully unified two things that seem separate, the result was more beautiful and simpler than anyone expected. Maxwell unified electricity and magnetism and got light as a bonus. Nobody predicted that. Einstein unified space and time and got the equivalence of mass and energy as a bonus. Nobody predicted that either. When the electroweak theory unified electromagnetism and the weak force, it predicted the W and Z bosons, and they were found. When quantum chromodynamics described the strong force, it predicted that quarks could never be isolated, and that has been confirmed. So the pattern is unification works, and it gives you more than you put in. That is encouraging. It suggests that a deeper unification is possible, but it is not guaranteed. Nature does not owe us a simple theory. Nature does not owe us elegance. It could be that the underlying structure of reality is messy, or complicated, or beyond our mathematical tools. We do not know. And the honest answer, the only honest answer, is that we do not know. But not knowing is not the same as having no hope. Not knowing is where the adventure begins. Every great discovery in physics came from confronting the unknown, from looking at a puzzle and refusing to accept that is just the way it is as an answer. Newton looked at the apple and asked, "Why does it fall?" Faraday looked at a magnet and asked, "What is going on in the space around it?" Maxwell looked at Faraday's field lines and asked, "Can I write an equation for that?" Dirac looked at Maxwell's equations in quantum mechanics and asked, "How do I make them consistent?" And each time, the answer changed everything. So what is the puzzle today? The puzzle is this. We have a theory, the Standard Model, that works magnificently but is clearly not the last word. We have a theory of gravity, general relativity, that works magnificently but refuses to play nicely with quantum mechanics. We have an enormous chunk of the universe, dark matter and dark energy, that we cannot explain. And we have a collection of free parameters, unexplained numbers, that we have to put in by hand. Somewhere in those puzzles, there is a clue. Somewhere in the mismatch between what we know and what we do not know, there is a new idea waiting to be born. And it will probably come from a direction nobody expects. That is how it always works. Now, let me be very careful here. I do not want to leave you with the impression that the Standard Model is broken or wrong. It is not. It is correct as far as it goes. The point is that it does not go far enough. It is like having a map that perfectly describes your city but is blank beyond the city limits. The map is not wrong. It is just not complete. And I think that is fine. In fact, I think that is wonderful, because it means there is more to discover. There are more surprises waiting. The universe has more secrets to give up. And for someone like me, someone who lives for the thrill of understanding a little piece of nature, that is the best news possible. If we already had the final answer, what would be the point of getting up in the morning? Let me tell you something about the way I think about these things. I like to imagine that nature is like an enormous chess game. The gods are playing, and we are watching. We do not know the rules. We do not even know all the pieces. But by watching long enough, watching carefully enough, we can figure out some of the rules. We see a bishop always moving on diagonals, and we say, aha, I think I have a rule. We see a knight making those strange L-shaped jumps, and we say, that is a different kind of rule. And bit by bit, move by move, we piece together the game. And the beautiful thing is that every rule we figure out helps us predict the next move. And when our prediction is right, we feel a rush of excitement because we have understood something. We have uncovered a piece of the game. And when our prediction is wrong, we feel an even greater excitement, because that means there is a new rule we have not yet found. That is the spirit of physics. That is the adventure, not the final answer, but the search itself. Now, I want to come back to the equation one more time, because I want you to see it from a certain angle. The standard model Lagrangian, that big, complicated-looking expression, is really just 4 lines. 4 lines that capture 3 forces, 12 matter particles, the force carriers, and the Higgs mechanism. And each of those lines has a meaning that we can state in words. The first line says, here are the force fields, and here is how they propagate and interact with each other. This is the line that describes gluons interacting with gluons, photons doing their thing, the W and Z bosons. The second line says, here are the matter particles, and here is how they feel the forces. This is where you see the quarks responding to the strong force, the electrons responding to the electromagnetic force, the neutrinos responding to the weak force. The third and fourth lines say, here is the Higgs field, here is how it interacts with the other fields, and here is the non-zero vacuum value that gives particles their mass. 4 lines. That is the universe. Well, most of it, the part we understand. And here is something that strikes me every time I think about it. Every line of that equation is dictated by symmetry. You do not get to choose the interactions. The symmetry tells you what they have to be. You do not get to choose which particles interact with which forces. The symmetry tells you. The only freedom you have is in choosing the symmetry group itself and in choosing the values of the coupling constants and masses. Everything else is fixed. That is extraordinary. It means the universe is not some arbitrary collection of random rules. There is a deep mathematical order underlying everything. And we can see it, we can write it down, we can test it. But here is the tantalizing question. Where does the symmetry come from? Why? SU3 times SU2 times U1. Why not some other group? Why 3 forces and not 4 or 2 or 6? Is there a deeper symmetry that contains all of them? Is there a single mathematical structure from which the whole standard model emerges as a consequence? That is the dream. One symmetry, one equation, one Lagrangian, from which everything flows. Not just the 3 forces of the standard model, but gravity too. Not just the known particles, but dark matter as well. Not just the visible universe, but the whole thing. And I do not know if that dream is achievable. Nobody does. It might be that the final theory is simple and beautiful, or it might be that the final theory is complicated and ugly, or it might be that there is no final theory at all, just an infinite regress of deeper and deeper layers, like peeling an onion forever and never finding a core. But I will tell you this, the fact that we have gotten as far as we have, that 12 matter particles and a handful of symmetries can account for every experiment ever done in every laboratory on Earth, that we can write down one equation that predicts the magnetic moment of the electron to 12 decimal places, that is not nothing. That is a clue, a very big clue. It tells us that the universe is comprehensible, that it has structure, and that our minds, these 3-pound collections of neurons that evolved to avoid predators on the African savanna, are somehow capable of grasping the deep architecture of reality. That, to me, is the most astonishing fact of all. I want to leave you with one more thought. The principle of least action, the idea at the heart of everything I have told you today, has a curious property. It is not really a principle of least action. Technically, it is a principle of stationary action. The actual path of a particle is one for which the action does not change to first order when you wiggle the path slightly. Usually that means a minimum. But sometimes it can be a saddle point. The language is imprecise, but the idea is precise. And that idea, the idea that the laws of physics can be expressed as a variational principle, an optimization principle, has a strange philosophical flavor. It suggests that nature is, in some sense, optimal, not designed, not purposeful, but structured in a way that admits a compact, elegant description, as if the universe is the solution to a mathematical problem. Whether that is a deep truth about reality or just a reflection of the way human minds organize information, I do not know. But I find it beautiful. I find it exciting. And I find it reason enough to keep searching, because the equation on the coffee mug is magnificent, but it is not the last word. The last word has not been written. And somewhere, maybe right now, some young person is staring at a physics problem or an experimental result or a mathematical structure, and they are about to see something nobody has seen before. They are about to find the next piece of the puzzle. And when they do, the picture of the universe will change again, as it has always changed, becoming more strange, more wonderful, and more beautiful than we ever imagined. I would love to hear what you think. If you could add one thing to the Standard Model, one thing that you think is missing, what would it be? Share your answer and let us have a good argument about it.